So one of the nice things about where modern sort of web GIS has gone is you don't have to be a desktop GIS wizard to make use of these maps and do the sorts of assessments. We can do them by hand like we're doing, but you can also do them in a web browser in a lot of cases. As an example, this is the national map viewer that USGS runs, and it's got a bunch of really simple tools in it. You can load up on this layer here. I've got a base map loaded that has contours. You get a basic lay of the land. Yes, they're pretty coarsely spaced. These are 200 or 400-foot contours, it looks like. No, sorry, 200-foot contours. Um, but you can switch out things. You can switch out the base map right here so that you're looking at, for example, the 7.5 minute quads, which in this case is telling us right away, like, oh, yeah, cool. Okay, so this is a more important road. There's a landing strip here. I don't know if we realize that. It shows up that there's this wilderness boundary, some pack trails, right? There's a power line, it looks like, running in through here. So these are quite helpful right out of the gates. Other things you can do, there's a measure tool, so you can, measure distances. So here it's okay, that valley bottom is 880 feet wide roughly. You can use this profiling tool, that next button over. And the profiling tool, you can pull off an elevation profile. And as we mentioned in the previous presentations, there's other ways of doing stuff, more involved GIS tools like VBAT and RCAT, but that can also give us some of these insights. What you do need to think about is evaluating risks. And this is a risk matrix that Timmy Mandish from the NRCS and Jeremy Maestas and some of their engineering team got together and came up with for low tech. And it runs through, you can find it in Appendix 3D of your manual, and it runs through and just asks you to look at, areas adjacent to the riverscape, what's the land use, and you score them, right? And you kind of get a green light, for undeveloped range or forest land settings versus a red light for being immediately adjacent to developed. Similarly for the land use within the valley bottom. Stream order and waitability, basically waitable streams being pretty easy going versus, non-waitable streams being something you need to think a little more carefully about. There's also a number of things just related to the landowner or land manager's willingness to work with process, really. So channel change and floodplain reconnection are those things that they're willing to allow the space for the riverscape to do that, or they're unable to give that up. Willingness to allow wood accumulation and or beaver dam activity to take place. And then adaptive management. And so this helps just sort of screen, and if the answers to these questions isn't the same throughout your riverscape, you have a reach break, right? So that you can differentiate these things. So it's really helping us get at, instead of it being an all or nothing, right? Stage 0 or nothing, the whole valley bottom. Finding out whether or not maybe we're dealing with a stage 8 versus a stage 0 situation. And if it is stage 8, let's get very specific about how much is accessible and how much is inaccessible to become active. Next, what we're going to do is we're going to map some of these anthropogenic constraints, admittedly with just the limited photographic and map-based evidence I'm giving you. So the second part of what you've printed out, I want you to go and I want you to map the infrastructure risks. And I want you to start, I'm just giving you this as just another view, another aerial photo. But what I want you to do is I want you to start by mapping the buildings, okay? I'm gonna pause for 5 seconds, let you do that exercise as long as you need. Okay, I've just shown what I've mapped here. There's a few houses, an outbuilding, and this is actually a pole barn. So you can make an assessment if you want. Right here, I've just colored them all red. If I wanted to assess these, we could do that a little bit later. But right now, let's just map some of the infrastructure. So now we can map the roads. And so what I want you to do, actually do kind of make a little bit of an assessment, if you will. So if you find the roads, and just to what degree are those roads at risk from the riverscape? I'll give you 5 seconds. You can pause the video and do your drawing. Okay, so here's one main road coming in, and I've, probably up here, I probably could have got away with coloring it green, but all through here, I colored it yellow. And the reason I did that is because, yeah, maybe it's right on the edge of there, so it's something I should be aware of, its proximity. And here it's coming across the valley bottom. It looks like it's built up, probably on a levee, but yeah, seems to be a fairly well-used road, and so presumably pretty reasonable. This one, it's dipping down in the valley bottom a bit more. There's a bridge crossing, comes up over here. It's sort of critical access for these houses. So yeah, and you can also score, the bridge crossings separately. But I'm not seeing any examples of like big run out splays or, evidence in the aerial photos of what looks like flood damage. So those are definitely areas I'd want to take a look at when I'm out. These roads, no big deal up on the hillside. There's also these dirt roads down here, seem well out of harm's way. Other than maybe the intermittent fan, but not at threat from this riverscape. These ones coming down in, probably also not a problem, but they are in the valley bottom, so we'll pay attention to those. And there's another little road up here. There's also an airstrip. It appears to be disused, but it's hard to say, so we'll note that. And one of the things you can get off the USGS layer is real good is canals. And so there is a diversion, point of diversion upstream here. It's not clear on whether it's actively used. It looks like it came in and at one time must have been used to irrigate this area. It doesn't appear, to be under cultivation or irrigation necessarily right now. And so the next thing that you can do is just make a judgment call about the areas adjacent to the riverscape. So outside of the valley bottom, color these by whether or not you think it's an area that's developed, an area that's in crop pasture or hayland setting, or in forest land setting. So I'll give you 5 seconds to pause the video. So what I came up with is on the different areas. I flagged this up as, developed, so kind of got to be aware that it's there. Just because I've drawn it as red doesn't mean that, we can't do anything. It's just we need to be aware that this is here. Nothing to worry about on this side at all in terms of our land use. Similarly on this side. Similarly all around here, right? So pretty straightforward. It's just really this one area to pay attention to. We can play the same game in the valley bottom. So why don't you go ahead and do that? I'll give you 5 seconds to pause the video and then start it up when you're done drawing. Okay, so we have valley bottoms and adjacent areas does not contain infrastructure of concern or contain some infrastructure but would not be negatively impacted. So consequences of impact will be low. Or consequences would be unacceptable. So I've just flagged up this upper section like, yeah, I mean, go for it. Nothing to really worry about. A little caution around the road here. On Coburn Creek, there is this whole area, and if it's kind of being retired and not used, maybe we could rethink it. But I at least flagged it as something to think about. This whole area called all green. Again, little caution around the road, and then downstream, I called it all good. And so really what we're doing here is, this picture that we've looked at over and over again, what we're doing is trying to get at that question: how much is in play for restoration? And the answer to that question is what we consider recovery potential. And so in pink here, this is how much could be in play. And recovery potential, this is basically the valley bottom minus whatever we have to avoid, infrastructure we have to avoid that's come up as risk. Okay. So on this previous slide, right, maybe the recovery potential in the Coburn Creek is a lot less of the proportion of the valley bottom width if we are deferential to this. This would be a conversation with the landowner or manager to find out what their intentions and concerns are for that area. Or maybe the whole thing, could be in play. So again, recovery potential is the combination of you take the valley bottom, you subtract away the stuff that's risky, and then you also have to make a judgment call, and we'll get to this a little later, about what could be in play given the flow regime, given other sort of external, forcing conditions. Maybe you have a bunch of diversions upstream and there's just not the high flow stream power that there used to be. Maybe it's impounded upstream, the reservoir is a different hydrology. There's a variety of things beyond just those local land use risks that could limit the recovery potential. Maybe if you're looking at wood, you just don't have the woody resources because land use has been converted, for example. So remember how I said that valley bottoms have two components at tier 1? Those components were basically the blue and the green, the active channels and active floodplain. Yeah, that's sort of true, and is true if what we're dealing with is a completely intact system. So when you have intact conditions, systems that haven't been anthropogenically impacted, the maximum you would expect is for 100% of the valley bottom to be active floodplain and active channel. Now, it may fluctuate. You may have areas that are temporarily inactive. We differentiate those inactive floodplains from terraces. Terraces are abandoned floodplains from a bygone, flow regime, from a like these are, think flow regimes from 500 years ago or more, not contemporary natural flow regimes. Okay, inactive can happen. Let's say these beaver dams went away, and there's not as much forcing up onto the floodplain, and so it becomes inactive for a while. It sort of switches off. That can happen naturally, and these things can come and go, and they can be ephemeral in their boundaries. But the upper limit is 100% when it's in good condition. So this is another way of looking at that, right? So I might have on the left really good recovery potential, but right now, in terms of indicators, you could look at evidence of inundation, high stage flow indicators, etc. But another good indicator is just riparian vegetation, right? Where is the vegetation being supported that is suggestive of that regular activity on a floodplain? The boundaries for valley bottoms between the area that could plausibly flood and not are pretty reasonable, pretty clear, okay? The boundaries between active channel and active floodplain, that's bankful, right? As squishy of a concept as that is. The boundary between active floodplain and inactive is a little squishier still. Maybe a lot of areas, something on the order of a 5 to 10 year recurrence interval flow, right? It's got to be, it doesn't have to be flooded every year, it doesn't have to be flooded year round, right, to be active, but it needs to be getting that flood disturbance, that flood pulse regularly enough to be considered active. Rarer events, 50-year events, 100-year events, probably not necessarily falling within the realm of active. Okay. So we contrast that with over here where the recovery potential and what's inactive, this is inactive because of land use. So when we map inactive versus active, that's really a statement of in the current conditions, where are things going, right? What is getting in play? And that may be, these people may not like it, but there may be areas that are getting flooded every year that they're fighting, that have infrastructure. So that one's a little less subjective, even though that boundary can be, like I said, squishy. By contrast, the recovery potential really is a judgment call. That's a judgment call, and that can change over time. It's a judgment call given what the land use, the land managers want. It's a judgment call that could change, say, post-flood. There's things that may be politically impossible prior to a devastating flood, and after the flood, people may be tired of fighting that fight. And so instead of just going back and doing the same thing post-flood, there's often an opportunity to rethink how we're managing those riverscapes and expand that footprint. So when Nick Weber talks after this, we're going to get at this question of whether or not the entire valley bottom is accessible or just part of it. And right here, what you're seeing is in yellow, the valley bottom, and then in pink, we're seeing this recovery potential. And one of the important points to make is that it's not actually, as I listed up here, the entire valley bottom. Well, what's the reason for that? The reason is because there's a property line right here, okay? And this is in a very poor condition here, where it's locked into, it's in the Riverscape evolution model, a 2. And so you're going to have to really get up and out of that ditch and really get some lateral migration. And so we're just not thinking that that's all that realistic for getting up onto this surface. Now, if the upstream property is acquired, you could really easily bump out over here and then flood this area. And so the recovery potential could change. But for now, it won't. Also down here, there's actually, within the valley bottom, a house that was built. And so the recovery potential, yeah, I mean, this area could all go and be engaged and flood, actually, technically pretty easily. But we're not going to promote that, and we're keeping that off limits because there is a house there that needs to be protected, okay? What we're seeing here is subsequent treatments through time. This is medium term after 1 to 2 floods, long term after 2 or more regular kind of floods, typical floods, or a large flood, right? So 5 to 10 years. And it's showing in red a diminishing amount of structure needed to keep pushing that. So that's hinting at the design. We'll get there later. But for now, just think about mapping your space by finding the valley bottom, mapping the current inactive, active surfaces within. That's an expression of condition. And then looking at the feasibility based off a combination of risk and what's possible within that system of recovery potential. So opportunity is defined by that gap between condition and recovery potential. And your job as a designer becomes thinking about what does it take to close that gap and how long, how many treatments might it take. I do want to point out that this logic that we're talking about of trying to map where infrastructure and land use constraints and stuff are, it's actually baked into some of our models like BRAT as intermediates. So things like distance to railroads, roads, bridges, culverts, diversions, canals, mapping intensive land use. Those are all intermediate layers in BRAT, which are really useful by themselves. However, when considering a specific risk, so let's say in the case of BRAT, whether or not beaver could cause problems to that infrastructure, this is not a realistic map of risk, right? This is a map of where infrastructure is. What you have to do is look at where is there high capacity to support dam building activity by beaver, and how does that align with these red areas. And if you do that, notice how much less red area, right? So a whole bunch here, right? This is 270 miles of perennial stream. It turns out only 15% of it, mainly on these main stems with roads, are areas we need to just pay attention to. There's a bunch of it in this intermediate category, and a bunch in minor, and over half in negligible. So that's, and you could play with the knobs on where your tolerances for risk are, but out of the box, Barat takes a very conservative view of this, and you can use that to sort of prioritize and look at really low risk areas. If you're trying to come up with, reach breaks for these questions that we're working ourselves through at a large watershed scale. This is a Huck 8, an 8-digit watershed. If you want some more information on BRAT and on those things, especially those intermediate layers, there's a link here, and so you can go in, and this is on our capstone restoration design class and walks you through some of those details in a specific project context. Well, let's see here. So we've done our inventory of resources. Now we're going to analyze that resource data and really we've hinted at, but get directly at these two questions. What are the current conditions and what's the recovery potential? Okay. So, and therein, we need to focus on the processes that can sustain wood accumulation and or beaver dam activity. So there's a lot of text. This is from page 100 of the design manual, but these are really fundamental questions. So I'm going to take our time through it. There's two key questions up top here that we need to consider from two perspectives. So those are, what's the current riverscape conditions? What's the recovery potential now and what it could be? And then we want to get into visiting those questions from sort of a hydrogeomorphic perspective. Is my channel and floodplain well connected? And and also visiting this from sort of a vegetative perspective. In the case of this structural forcing, is it likely that a self-sustaining source of woody structure can be restored, i.e. the riparian and beaver ecology question? So this first question, are my channel or channels and floodplain well connected? This is interesting, right? If we come back to our simplified riverscape evolution model, basically if I'm in this sort of stage, we could give it a red light. If I'm in these sort of stages, we give it a yellow light. So poor, moderate versus good, right? I mean, that's the kind of scale you want to dumb this down to. Now, how rigorous of an analysis you use to come to that call, that's up to you. If the stakes are high, if the stakeholders are really nervous about stuff, maybe you put more effort into that. Maybe you bring in some experts, helps if you need it. If the stakes are low, the significance of getting this, maybe I'm that, aren't that big of a deal, then stick with something simple. There are approaches, more sophisticated approaches. This is an example Andy Hill and Steve Bennett worked on for, this is Panther Creek drainage in central Idaho. This is an assessment that they did for the tribes, and they used river styles. It's the same folks, Gary Brierly and Kirsty Friars, who put together that system. And there's a little bit more sophisticated analysis going on here to arrive at a map of geomorphic condition, again, in stoplight form. So there's a lot of detail behind this, but it's synthesized into a stoplight form, versus recovery potential. And in the river styles framework, recovery potential is not what I was showing you before in terms of that map. Instead, recovery potential is kind of the propensity or the ability of that reach to improve its condition. So if it's already in an intact or good condition, it's showing up as blue. The areas in green are the areas with high uplift potential. Yellow, sort of moderate uplift potential, and red is something less. So slightly different take, but there are more sophisticated techniques. You have to choose the right horse for the course that you're racing on. Okay, so that's a way of looking at geomorphic condition. In these videos, which are available again on the capstone design class, I show how you can use the channel evolution model and basically the proportion of active width as an expression of stage. and then also an expression of geomorphic condition. So there's a little worksheet and some stuff on there if that's of interest to you. More important thing is just, really engaging and thinking about these questions and, investing in a more sophisticated analysis only if it's warranted, not just because you can. I like to default always to the simplest thing that I can get away with that's fit for purpose. And err on the side of caution there, but, try and not just break the bank just because I can. This question of is the flow regime present to do the work is one that you could spend years, trying to study the hydrology and gauge a place. You can also just go to USGS stream stats in other regions, other countries. If there is available gauge data, you can build your own regional curve. But really, all this is applying a regional curve everywhere. And all you do is pick a pour point, the outlet of your watershed, typically at the top of your reach or the bottom of your reach, and then it'll immediately delineate a watershed for you. And then you can continue, and you can then get out some simple flow statistics. These flow statistics are all just based off of all a regional curve is. It's just, let's see if I can make one for you here. You basically just have a graph, and you have discharge and then drainage area, upstream drainage area. So right here, this guy's got 0.79 drainage area. And then you're just going to have a bunch of dots, right, that are basically showing that for some flow curve, right, Q, discharge, that, as drainage area increases, discharge increases. Those would represent, let's say, like a Q2, a 2-year recurrence interval flow. Someone fits a curve through that. That curve is what gets applied to give you this stuff, okay? So it's not, it's not the most, let's see, I think I can, well, we'll just turn off our pin. Erase all ink, there we go, and turn off my pin. This is just readily available. You can spit out a nice report. I walk you through it for a specific example in a video here if you need that demo. Models like BRAT are taking and leveraging this data and using it to produce for various flow statistics, Q2 map, base flow map, Q50 map, etc. This example right here, high flow represented by a Q2, high flow stream power in watts are the units, but then it's symbolized in terms of a question that BRAT tries to answer, which is, if dams are built, how likely are they to persist through a 2-year flood, basically. And so these are roughly, the dam's going to persist no matter what, potential dam breach, potential dam blowout, or, it's definitely going to blow out. That's just based off of stream power. So we can get slope off these drainage networks. So that's S. The Q is the Q that we're getting off those regional curves. Gravity is a constant, and density of water is a constant. So pretty simple way of looking at these things and mapping out nuances and differences in your flow regime. So that gets at our sort of hydrogeomorphic, sort of perspective on riverscape conditions. In terms of recovery potential, one little wrinkle you could add in here is if climate change was projecting, differences in that hydrology, you could try to take that into account. But that's a little more advanced. So let's take a moment to consider that next set of questions. It's all about, are the woody vegetative resources present to support the processes of wood accumulation? So one of the things we can do here, we can look at sort of riparian and upland vegetation. We are working on a model called RAT, the Wood Restoration Assessment Tool. It's not ready for prime time. It's in a proof of concept and development phase, but it's kind of this. It would be the sister to BRAT, and it would try and directly address this. We have one that indirectly addresses it, and it's our riparian condition assessment tool. And one of the primary outputs of that is what we call a riparian vegetation departure. And so in this catchment, you can see most of the 3,600 kilometers of streams in the upper catchment, which happens to be wilderness extending up into the Wind River Range. It has negligible departure, and then a bunch of stuff in this intermediate range with various land uses. There's some significant departures, okay? So what is that algorithm doing? What it's doing, and we happen to be using 30 meter pixel Landsat data, actually a Landfire derivative, but you could use higher resolution stuff if you had it. This is a map of existing riparian conditions, okay? That's a map of estimated historic. How does Landfire do it? Does it know what was there? Well, this is a state and transition model which attempts to predict what you might have found there historically, right? It's not perfect, but it's better than assuming that riparian would have been wall to wall in the valley bottom. It's based off of looking at the existing vegetation communities that are native and looking at, aspect, soil conditions, all the sort of, things you can get off of morphometrics, soils, etc. And it's trying to estimate what's going on there, okay? So all we do is go into these places. We actually calculate in different valley bottom segment cells what the proportion of loss is from existing to historic, and then we can go in and say, okay, that reach had a large departure, this reach has a significant departure, this reach has a minor departure, etc. Okay, so in a nutshell, you input your perennial stream, you derive a valley bottom, that's VBET. You break that valley bottom up into different segments. Here they're just broken up into like 300 or 500 meter segments. You can also break them at, for example, property boundaries, bridge crossings, road crossings, etc. And they're already broken at tributary junctions and confluences and diffluences. And then you map the existing vegetation types, the historic vegetation types, and how many of those would be considered riparian. And then you calculate these departures, and you can do this at really broad spatial scales. So that's kind of a cool way of approaching the problem. That's just riparian vegetation departure. The RCAT has a riparian condition model that also looks at floodplain accessibility, which it's similar to active floodplain versus inactive. What it's actually doing is it takes the valley bottom and then it looks for roads and levees that cut off access to the other side of the levee or the road. And that's how it estimates floodplain accessibility. Then there's land use intensity, which is pretty easy to summarize in those same cells. And we combine those and we can get sort of an overall assessment of condition. So don't get obsessed with the tools. Don't get obsessed with these models. A lot of these tools are, peer-reviewed, scientifically vetted, good research grade GIS tools. They're not professional grade tools that are easy to use. You kind of have to roll up your sleeves and kind of know what you're doing to get them to dance. Now you can hire other people like our lab to do those assessments for you. And what we're working on is trying to get funding to turn these, skip right past what we call professional grade, and trying to turn them into commercial grade tools, or at least what we call production grade tools. Production grade tools that we can run on the same stuff that Netflix runs on. We can run on cloud services, basically, run these at broad scales, and then make them available to people. A commercial grade tool would be building an app that most people, 95% of people would never pay a penny for, but works really good, say like Strava. And then a few people want a few more bells and whistles, and that's what subsidizes and pays for it all for everybody. what that means, what that translates to, is trying to turn these tools into things that you don't need to be a GIS expert to use, that anybody can engage with. So there's a little bit of information on this link here if you want to watch a video on RCAT. Now let's move on to that question of could beaver dam activity be supported? So you kind of did this exercise, right? You sort of mapped where beaver dams were, right? So there's a bunch of beaver dams right here. So one easy way, could beaver dam activity be supported? Well, if you see beaver dams, clearly yes. The alternative to that, this is another view in there, and a few more beaver dams. The alternative to that is brat. And although we've spent a bunch of time alluding to brat, we haven't really done brat or talked about it. I'm going to just take you to brat real quickly to the website here. And there's a little fact sheet, and there's a bunch of stuff here. So I apologize, this is so buried. But you come into the John Day workshop, and you scroll down, and what you're going to see, there's various things here, but I think it's, yeah, right here. So there's a bunch of presentations. You can go into these presentations, and there's this capacity form. And this capacity form is basically brat. And you answer a question about the suitability of streamside vegetation, the suitability of riparian and upland vegetation. Then you answer some questions about, can they even build a dam at base flow? Does it typically hold up? And a little bit of questions about the extremes of really low slopes or really steep slopes. And then what you get, so this is just the exercise doing that, what you get is, these slides are going to just walk you through how you answer, how you fill out these forms, right? And so you might want to take a look at that. The actual form is right here, this BRAT CISF form. And it's pretty simple. I mean, this is a non-fuzzy inference system version. This is just an inference system, a rule table of BRAT. And we're working on trying to get a Citizen Beaver app that would have BRAT in it so that you could just do this on the side of any stream, or you could do it from the desktop. It's kind of a nice little exercise. So that's worth being aware of. Mapping beaver dams is a really straightforward and extremely useful exercise to get a handle on. And so there's a lot of ways you can do that. When you have beaver dams mapped, it helps you look at, instead of lumping together where there's, say, conservation and restoration opportunities, the context of areas that have high capacity and already have a lot of beaver dams, so like that Musgrove Creek, might highlight some areas where you're in a conservation situation versus areas that, that might have good conditions but no real beaver dam activity, and those might be your areas for restoration opportunities. So mapping dams, mapping jams, this is really useful, and there's details of this on that capstone site. So in conclusion, what we have is a low-tech restoration planning approach that's following the conservation planning process. We've highlighted some specific considerations for low-tech in terms of those green and yellow boxes. And we're providing clear exit points where, if in the planning and design process you realize that low-tech actually doesn't make sense, you can exit gracefully before wasting your time. One example here is this also integrates with the principles, and what I'm showing in this picture, this is actually a project with Jay Wild, on a little tributary to Birch Creek. This is Mill Hollow, and we built 3 BDAs. These were actually our first postless BDAs, beaver dam analogs. And what happened, and here's a 4th one that was built, there's a primary dam that was built, some secondary dams, etc. And you can watch Jay tell this story. There's links off of the website. And what happened is beaver came in, co-opted those dams, raised the crest elevation, took over, just transformed this place. All this down wood is all harvested aspen. And these dead conifers, they're dying because they've encroached into the valley bottom, and now water tables are up. What happened? Well, all the black dams happened. So a few BDAs released some translocated beavers into these. They took up shop, made a difference, and now we're well over 150 dams. So pretty neat. Anyhow, that's planning in a nutshell, and I hope you found that useful.